Okay, let's start the session. Good morning, everyone. Welcome to the second day of the Open Data Workshop. In this session, we will have Hirotaka Yuzurihara-san to give an introduction on the data quality. Let's welcome him.
Good morning, everyone. Thank you very much for giving me opportunity of this presentation. I am Hirotaka Yuzurihara from Kagura Collaboration. Previously, I was working on the data analysis, such as searching for CBC signal and also develop a methodology. Recently, I'm working on the Kagura side for the detector characterization. Our task is to provide the data quality information for data analysis people. So these topics. So okay, I will start. So many slides were copied from past presenters. Thank you very much. And for previous workshop slide, please check this link. And at first, this slide is Sawada-san's slide yesterday. And at first, I would like to point out what is our position of this talk in this data analysis flow. So here is a interparameter such as LIGO, Virgo, Kagura, and interparameter output data and output data, storing data. And this blue region is for search pipeline. They analyze the data, and yes, and the position of this talk is between them. So between output data and search data. So it is important to okay. It is known that some portion of the data have trouble on data quality. It makes worse the sensitivity of the gravitational wave data, such as time domain, frequency domain, and the time frequency map. And next, okay. Next is the main topics of this presentation. I explain about the noise artifacts in storing data. I will introduce two examples, grids and lines. And after that, I explain about mitigating noise artifact. And also, I explain about the monitor tool, public summary page. So first topic is this: what does gravitational wave data looks like? So page 6. So left bottom figure is simplified LIGO interparameter, and this interparameter is same as almost same as LIGO and same as LIGO, Virgo, Kagura. And as you know, the gravitational wave is detected by principle of the Michelson interparameter. So input laser from left side to beam splitter, and it enter to beam splitter and splitted perpendicular way, X arm and Y arm. And it propagates 4 kilometers, and there's a Fabry-Perot cavity to enhance the interferometer, enhance the sensitivity, and reflected and interfere at the beam splitter and go to output port and interfere there. And the output recorded at the output port is a voltage unit. So calibration group calibrates the data to strain unit, a strain. And the right top equation is a definition of the strain data. H of t is a strain, and the right side is a definition of the strain. And when gravitational wave arrived to telescope, as Jonathan explained yesterday, X arm and Y arm shrink or stretch, and the effect appear on the output port. So we analyze the data. And this strain data is available GOSC page. So yeah, during this workshop, we are reading data and analyzing data. Okay, next is one of the example of the time domain data. And this is available on GOSC page. And this is a LIGO-Livingston case. And x-axis is a time, y-axis is a strain. And this is data of O3A. And please check the y-axis strain. Value is a 10 to minus 18 order, so very tiny amplitude. And GoSquare page provides us the two kinds of data. One is about sampling rate. One is 16 kilohertz. Another is 4 kilohertz. So you should select which you need. If you are interested in the high frequency, you should use the 16 hertz, kilohertz. And if no, please use the 4 kilohertz. And also, please again in the top image, what do you see? This is a very typical data, so it is difficult to obtain specific information from this data. And what I obtain is this data is dominated by 9 hertz noise because here, during 1 second, data oscillates 9 times. So it is not enough to see just the time domain data. So next slide, page 8. We use the frequency transform to convert time domain data to Fourier domain data. And so this top image is called sensitivity, or sensitivity means not just a Fourier spectrum. This sensitivity, amplitude spectrum is often used to represent the sensitivity, and I explain what's that. So definition is right bottom side. ASD is defined by square of power spectral density. So I call PSD. So PSD is defined by as like this. So this capital XF is a Fourier frequency spectrum, and yes, and there's a bracket. This bracket is called the ensemble average, and yes, we take an average to compute a PSD. And one of the way to average is taking a mean. But sometimes it does not work because later I explain about the non-stationary noise. And if there's a non-stationary noise in the data, that affects taking a average, and the result will be biased. So to reduce the effect of bias, not usually, often we use a median. And in the case of GWPy, it is a default, so now you don't need to care. And okay. And another advantage of this ASD or PSD is this T. T means duration of the data, so length of the data. So divided by T means convert to density. And because of this density, we can compare the another length of the data. So page 9. This is another example of the time domain data. And this is O1 data, yes. Top one is raw data, so raw data. And the bottom one is band passed data and noise notch filter data. And here we focused on the 10 hertz to 100 hertz by applying a band pass filter. And also 60 hertz was removed from data because 60 hertz is usually dominated by power line. So now we are not interested in such frequency, so we removed it. And this kind of things is called signal processing. And also this is available. I mean, we can do this by using GWPy. GWPy, yes. So next is okay. Wait a moment. So if you focus on top image, this is the raw data. Nothing special looks like not happening. But if you see the bottom data, this is the same data, But after applying a bandpass filter, you can see the bump around 10 seconds to 12 seconds. So I'm not sure the origin of this, but this kind of bump happens. So we focus on this. So next, page 10. So top one is the same one, filtered data. Bottom one is the amplitude spectrum density of same data. So you can see the two colors on the plot, and orange one is the averaged ASD from all the data, 20-second data, but the blue one is a part of data, computed from a part of data. So, okay, this is a movie mode, and gray region is moving. So blue spectrum is computed from such kind of small portion of data. And when gray region arrived at 10 seconds to 12 seconds, you can see the bump around this 10 hertz to 100 hertz. Wait a moment. Yeah, you can see the bump on the frequency domain. So this kind of non-stationarity noise sometimes happens. So important point is this bottom one. Strain data is not always stationary. So we should also consider about non-stationarity. And next, I explain about how we see the visualize the non-stationarity noise. So this is one of the example. And this plot, x-axis is time, y-axis is the frequency, and the color bar right side is called normalized amplitude. And normalized amplitude, roughly speaking, normalized amplitude means is a ratio of the blue ASD and the orange ASD in the previous this slide. So, okay. So yes, this kind of normalized spectrogram is convenient to find the excess. So if this data is completely stationary, blue ASD and orange ASD is almost same. So same over same means one, almost one. So this spectrogram looks like blue, almost blue. So almost unity. But this is different. So around 10 seconds to 12 seconds, you can see the yellow region. This is excess from stationary data. But this spectrogram also have a limitation on the resolution on time and frequency. Actually, this is many tiles, and that tiles have a value. And that tile have a same fixed area, and fixed time resolution and fixed frequency resolution. So if you focus on the low frequency region, you can see the tile, size of tile. But if you focus on high frequency region, tile looks like a very tiny because relatively, so it is better to change the tile size relatively. So one of the way is next slide, Q transform. At first, I explained about the Q transform. This is comparing with the Fourier transform. The basis is different. Basis in the Q transform is a sine Gaussian, and Q, and also Q is defined in the right top. Q is called the quality factor, and this it means how many times it oscillates before damping. So please imagine the bell in the temple, gong, sound continue long. This means high Q. But on the other hand, sound damping very quickly. So this means low Q. So and focus on the left top side. There are three types of the tiles. Okay, for example, this pink one tile with a high Q is a x-axis is a time direction. So for x-axis direction, long resolution, large resolution, no, low resolution, maybe low resolution, because high Q means it needs time to damping. So this kind of resolution is enough. On the other hand, in the case of low Q, so sound or signal dumps very quickly. So we need a very high resolution for time direction. Okay, and in the case, okay, and right bottom figure is a combination of such kind of tiles. So we compute this kind of transform by changing Q value and find a proper one or best one. And this top one is the same as previous result, time spectrogram, normalized spectrogram. And the bottom one is a result from a Q transform. So looks like better. And maybe, I guess this is a non-stationary noise caused by scattered light. Later, I will show you another example. Okay, next is page 14. So I talked about data quality, noise artifact in string data. Page 15. So in the perfect world, gravitational wave data looks like this. This is a hope, and top case is a no signal case, and this you can see the two line. This is a blue one is a Livingston data, and green one is a harmful data, and bottom one is one of the most famous signal called GW150914. And this is a first event of this is a first event. And yes, same as top one, we can see the data. And also, red one is a filtered binary bit black hole template, so waveform. And the right image is a Q transform of this left data. So top case, no signal case, we cannot see the specific characteristic structure on that Q transform. So yes, this data looks like very stationary. And bottom one is this data includes a gravitational signal, so we know. So yes, we can see the trace on by the gravitational event. So this is also a very characteristic shape. So this compact binary neutron star, compact binary coalescence make this kind of chirp signal, and to the merger, the frequency will be increased, and this kind of shape appeared. So, okay, then we should analyze the Q transform for all the data, and let's find this kind of shape. But if it works, it is okay. But in the real case, so string data is a non-stationarity. So I borrowed many plots from many papers. So left top, okay. Anyway, all the time frequency map, and yes, you can see multiple types of the non-stationarity noise. And important point is duration and also central frequency and also characteristic shape are different for most cases. So many kind of non-stationary noise. And okay, also this is the introduce of the glitch. And this kind of non-stationary noise is called glitches and continue short duration or middle duration. Okay, and detail I will explain later. So this is an introduction of the gravity spy, and it is a citizen science for glitch classification. So as we see in previous slide, there are many types of the non-stationarity noise, and this is a citizen science. So you can join this activity and contribute. This looks like this. So by clicking on website, so please visit this. And another non-stationarity feature is called line noise. And previous glitches affect wide frequency, broadband frequency. But this, compared with this line noise affects a very narrow band, usually less than 1 Hz, and persistent artifacts. So it affects long duration, for example, always there. And this slide was copied by Takahiro Yamamoto-san, so who presented yesterday, and he listed up several sources of line noises. So one is a 60 Hz power line and its harmonics. Yes, right figure indicator. Right figure shows a LIGO O3A amplitude ASD, and you can see the many spike-ish structure, and also sometimes we call comb, yes. And yes, this is always okay. And several sources are already identified, but several line noise cause still unclear. And I explained about the power line, and also violin mode of suspensions. So mirror are suspended by suspension and hold, suspended by fiber or wire, and the length of mass balance due to such kind of things, specific characteristic frequency line noise appeared on this ASD, or another source is environmental disturbance. And instrumental lines can degrade the continuous wave search sensitivity. Yes, that's right. Okay. And it is clear to see many combs on the lines in the data. So about known line noise, information are summarized on this GUOSC page, so please see that. And about noise subtraction for O3 dataset. So after data collection, we removed several independently measured terrestrial contributions to the detector noise. So in the case of LIGO, so they removed the calibration lines and also 60 Hz power lines, harmonics. So also we removed some additional line due to non-stationary couplings. And in the case of Virgo, they removed the broadband noise, including a frequency noise from the laser noise introduced when controlling the displacement of the beam splitter and the amplitude noise of the 56 megahertz modulation frequency. And the bottom one is an example before and after of noise subtraction. So you can see the effect of noise subtraction, effect of noise subtraction line noise. Okay, page 21. So next is I explain about mitigating noise artifacts. So until now, I introduced the non-stationary noise. And before starting observation run, interferometer experts try to identify the cause of non-stationary noise and remove the cause or source as much as possible. But still, some of non-stationary noise remains in the data of observation run. So to reduce the effect of non-stationary noise to the analysis, gravitational research, so we provide the data quality information with several categories. So this is a list of the data quality information. So at first, this data, this label, so there are several categories or labels, and this top one is data is available or not. So, and also there are several categories. And in addition to that, sometimes expert performs a hardware injection to the interferometer to test. And when hardware injection is ongoing, this such kind of information also provided in this data quality information. Then I explain the category one by one. So first category is called data. So when this data, when failing this level indicate that LIGO data are not publicly available because the instruments of the data calibration were not operating in acceptable condition. So such as the interferometer is not science mode. And the next category is category one, called CAT1, and failing data quality check at this category indicate a critical issue with key detector components not operating in its nominal condition. Nominal condition means such as expert is working or touching interferometer, so it should not call the science mode. So, and these times are identical for each data analysis group. So, as we see in the previous list, there are two types of the category for data quality information for CBC search or data quality information, so burst search. But about category one, same for CBC and burst. And times that fail category one flags are not available as LIGO open data. So next category is called CAT1, CAT2. And failing data quality check at this category indicate times when there is a non-understood physical coupling to the gravitational channels. For example, high seismic activity. So this is called so before starting observation run, experts try to identify the cause of the non-stationarity noise. But if they know that there is a non-stationary noise, but they cannot identify the sorry. And category 3 is failing data quality check at this category indicator times when there is a statistically coupling to the gravitational wave channels, which is not fully understood. So category 2 is we know the cause, but category 3, we don't know the concrete cause, not fully understand. And data quality levels are defined in the cumulative way. Time which fails a given category automatically fails all higher categories. So higher category means category 3, and category 3 is severe than category 1. And the data quality categories are defined independently for different analysis groups. So if something fails at category 2 burst, it could pass category 2 CBC. So if this is because compared with burst search, CBC compact binary coalescence signal continue longer than burst signal. So the interesting time duration are different. So next is auxiliary channels. So usually we record over 200,000 channels per detector that monitor environment and detector behavior. So we can use these to help trace the instrumental cause of glitches that pollutes the search backgrounds. So this plot is one of the example. X-axis is time, and y-axis is amplitude. And from top, storing data, and window speed sensor, and microphone. So you can see the several transient called glitch at the strain data. So on the other hand, also at the same time, we can see some non-stationary behavior on other sensors. So this blue one, for example, this blue one, we can see the coincidence between strain data and microphone. And also you can see lighter area. We can see the coincidence between strain and wind. So this will be hint for noise hunting. And for all three data, LIGO's auxiliary channels are publicly available. So please see this web page. So this is I explained about physical environment channels. So this is an example of the LIGO Livingston case. So actually, mirror or laser are installed in the vacuum chambers. So these are in the vacuum chamber, and at the same time, many physical environment sensors are installed at the site, and this is common for LIGO Hanford or Virgo Kagura. So we have many physical environment sensors. And here I introduce several examples. So green box means accelerometer, and this is an example of microphone or magnetometer, temperature, voltage monitor. So and also infrasound microphones. Many PM physical environment channels are installed and working for noise hunting. So here is an example of noise coupling. Yes, this is an example of the thunderstorms. So top panel indicate data of the accelerometer, and the bottom one indicate data of the spectrogram of the strain channels. And x-axis is the time, and so on the strain data, you can see several x's here, 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 and at the same time, accelerometer, we can see some coincident signal. So passing the thunderstorm, we observed the strong acceleration. So due to thunderstorm. And this is an example of noise coupling at Virgo data. And top one is a magnetic glitches, and the left of top one is an interesting one. So when airplane pass the Virgo around the Virgo, so it affected the strain data. And this right small box indicates a microphone. So we observe the coincident signals. Or another example is a scattering light or seismic glitches. So yes, there are many non-stationary noise, and it coupled with the strain data. Okay, so until now I explained about the data quality information. So and it is available on GOSC page. And here I explain about how to get data quality segments. This example is from GOSC timeline page. And at first, please visit the right top web page. And this is you can see here you can select run. So now S5, S6, O1, O2, O3, and O3GK. And please select which you're interested in. And next you select time, and you can directly input a GPS time, or you can select from a calendar. And okay, this is an example of the O3B data and for Livingston data. So after input all the information, please push this display button. So here is an example, and right top table summarize, for example, active time, and also duty cycle, and also number of segments. Duty cycle means a ratio. Ratio, and the segment means okay. Yes, these information are already okay. And if you want to see the concrete value, please select this ASCII and also this L1 push L1 data. This kind of text data will be displayed, and from left side, starting GPS time and ending GPS time, and duration. Duration of the how long this continue. And also this kind of segment bar will be shown, and this is a static, but if you visit the web page, this bar will move interactively, zooming up or zooming up, or you can download. So another example is how to get a data quality segment by using Yuzurihara. So example of how to find and plot data quality segment is summarized in this document, Yuzurihara document. And here is the actual code. So yes, if you are interested in other data or other data quality, please change this orange region. And here is an example. And this segment bar shows the availability of the LIGO Livingston data and Hanford data. And this top one indicates both are available at the same time. So top both means two detector available data. Okay, and this was just a plot segment bar, so we cannot obtain the concrete value. But if you run this code and if you print out this data quality flag, the concrete value will be shown. And here, known segment means a period which you referred, and this active means a period which both flags are active. So it means both data are available. And if you want to pick up the active segment, here you can do like this. And final topics is monitor tools. So yes, this kind of public daily detector status page is available online. And yes, please visit the top web page. And this is a date of the first event of binary neutron star. And at that time, this kind of sensitivity detector are working with this kind of sensitivity. And this is x-axis is the time, and y-axis is the detector. And this is the duration. Period is 1 day. So 1 day, 1 page. And this how you tick bar indicator in the detector is science mode. And this is a time series of the inspired range. And inspired range is a indicator, one of the indicator of how detector is very sensitive or not. So, and this inspired range indicates how far we can detect the signal from a binary neutron star on average. So, for example, in the case of Livingston, at that time, they could detect binary neutron star from within the sphere of 100 megaparsec on average. So also please check this web page. And this is a public daily detector page for O4A. O4A. Yes, O4A. So also it is available. And this is a O4B. So from April 10, we started the observation run, and now you can see the current situation by visiting this web page. And okay, final topics is the reference. So I listed up the useful reference for data quality. So yes, so that's all.
Thanks, Hirotaka, for the nice talk. Is there any questions?
Yeah, in the LIGO summary page, it seems that I did not see the information about Kagwa, where the Kagwa supposed to be merged into the same summary page in the future.
I hope so. Technically possible.
Hi, Hiro. Nice talk. I wanted to ask, what method do you use to remove 60 hertz line? The power line, exactly?
Method. Sorry, I cannot answer now.
Okay, sure.
Thank you.
There's a question online. So for data analysis, which category set of data is useful most?
It depends on what you need. So maybe you should start from category 1. But okay, I should show you. Wait a moment. It depends on what you need. And here is an example of the LIGO Livingstone. And please check the duty cycle, category 1, 2, 3. So category 1 is 77%, but category 3 is 76%. So very tiny data are removed. So maybe you can use category 3.
Is there any questions? Oh. Actually, I have a question. So, for the online search and offline search, did they use the different data category, or say this could be the second question? So, what data category do the online and offline search use?
In my understanding, so online search should finish very quickly. So maybe they use very basic data quality information. For example, data is science mode or not.
Okay, so for offline search, did they use a more refinement data quality?
Yes, and so this kind of data quality, I mean, it depends on case by case.
Okay, thank you. So, is there other questions? If no, let's thank Hirotaka again.